Hello and welcome to our presentation. My name is Theodor Ensbury and I am a simulation engineer at Claytex USA. Today we'll be looking at an FMI co-simulation case study where a vehicle model experiment created in Dymola is deployed and used in Simulink for control system development. To start with, we'll give a brief rundown of Claytex as a company before further elaborating on the specific aims of this case study. The vehicle model, control and export process will be explained before presenting the results of the study. Based primarily in the UK, but with satellite offices in the USA and South Africa, we cover all aspects of vehicle simulation, from internal combustion engines to driveline components, vehicle electrification, electrical and HVAC integration to vehicle dynamics, chassis platform modelling, and autonomous and ADAS simulations. Much of this expertise was developed originally when working with motorsports customers in Formula 1, NASCAR and IndyCar, but has been expanded to the OEM and Tier 1 sector as development practices have evolved. Working with Dassault Systèmes, we produced a VeSyMA suite of libraries and Modelica-based simulation library for use in Dymola. This case study forms a useful exercise in demonstrating the suitability of the VeSyMA library as a basis for distributed high-fidelity vehicle simulation. As a development exercise, case studies like this enable us to handle our products as would-be customers and understand them better from that viewpoint. This case study provided understanding into some aspects of the challenges of exporting our vehicle models and experiments as FMUs for deployment. To achieve those aims, a vehicle experiment complete with control model found within the investment product will be benchmarked with and without an ESC controller within Dymola to start with. Next, a vehicle experiment without the control model will be exported as an FMU and ran in Simulink as a standalone model in order to understand any effects of the export on the performance of the vehicle model. After this, the FMU was ran in Simulink with a Simulink interpretation of the ESC controller. With these results, comparison results were plotted with the FMU performance without ESC in Dymola and Simulink. Finally, a comparison is made between the experiment in Dymola with Dymola-based ESC and Simulink with Simulink-based ESC to better understand the challenges of interfacing models with the FMU. The experiment which forms the basis of this study is a cone slalom test, with the vehicle trying to navigate between the cones whilst holding a speed of roughly 31 miles an hour or 40 meters per second. The cones are close, only 50 meters apart. To make sure the vehicle is more unstable, an 80 kilogram extra trunk payload has been added. You can see from the animation of this experiment running in Dymola that the ESC is effective in keeping the vehicle under control versus no ESC. Models for this case study were taken from the VeSyMA suite of libraries, which is a complete vehicle simulation solution based in Modelica. It is comprised of a series of Modelica libraries based on the VeSyMA library itself with subject-specific extensions. The vehicle model used in this case study is adapted from a generic front-wheel drive compact segment vehicle model found within the VeSyMA suspensions library. As this is a full multibody vehicle model, it is capable of the full 6 degrees of freedom, therefore all pitch, roll and yaw is captured as well as lateral, longitudinal and heave motions. Looking into the subsystems of the vehicle, we can see that the Pajeca 6.2 tire model is used with an aerodynamics model capable of capturing the lift, drag and side force. Rigid subframes are used, as are ideal, so no compliance of bushings, multibody front and rear suspension models, double wishbone at the front and multilink at the rear. This vehicle template is also equipped with an electronic stability controller module. This is replaceable with a dummy model shown. The ESC communicates with the vehicle through the control bus, which is an expandable connector analogous to the CAN bus. Moving on to the other vehicle subsystems, a fixed mass fuel tank model is used, as is a mapped engine model, and no front engine auxiliary drive model is used. Therefore, no parasitic losses caused by things like alternators connected to the serpentine belt are modelled. A 1D rotational driveline model is used, featuring an open differential, connected to an idealized paddle shift transmission model. A pseudo-hydraulic brake subsystem featuring individual multibody brake models is used. The ESC affects the vehicle's dynamics through a pump model, which is controlled by signals on the control bus. This brake subsystem is termed pseudo-hydraulic because it is entirely real signal-based, i.e. there are no fluids being physically modelled in the subsystem. These simplifications have been made for simulation speed, as we are not overly concerned with the total vehicle fidelity for this case study. Any of these systems can be replaced in this vehicle model with higher fidelity ones, such as a fluids-based hydraulic brake model capable of capturing the full braking dynamics if desired. The electronic stability control algorithm responsible for calculating the corrective brake pressure at each vehicle corner used in this case study is relatively simple. An error between the vehicle's actual yaw rate and a theoretical desired yaw rate of the vehicle, which is based upon the steering angle input by the driver model and the understeer gradient of the car, is calculated. The yaw error then drives a PD controller to determine the corrective brake force used. Effectively, this means that the electronic stability control serves to control not only oversteer but also excessive understeer. Lookup logic tables dependent upon vehicle parameters such as lateral acceleration and understeer gradient determine the brake force distribution at each wheel. The algorithm described on the previous slide has been replicated in both Simulink and Dymola. Whilst the ESC models were validated against one another to produce the same outputs, there are modelling differences between them. The Simulink model, for instance, makes use of triggered and enabled subsystems to change the controller state, whereas the Dymola one uses logic tables to effectively switch off functionality by multiplying signals by 0. The Dymola ESC model was taken from the VeSyMA suspensions library. The experiment this case study uses as a basis was taken from the VeSyMA suspensions library. All elements required to simulate the cone slalom test outlined previously can be found in this example vehicle experiment, including the road model containing the driving line the vehicle is to follow and the atmospheric conditions of the simulation environment. Both these models are replaceable, enabling high fidelity ones to be easily deployed in the experiment if desired. The drive model is independent of the vehicle model itself, meaning the vehicle specification can easily be replaced without impacting upon the driver model settings by redeclaring the model. All VeSyMA vehicle experiments feature this same template. As the control bus has been declared at the top level of this model and connected to the vehicle model, this vehicle experiment can be configured into an FMU easily. As I mentioned earlier, the control bus is an expandable connector analogous to a CAN bus. As it is expandable, additional signals can be added to the bus easily, which is precisely the method used to produce the small family vehicle equipped with the ESC as found in the VeSyMA suspensions library. As the FMU we are creating for this example requires inputs and outputs into the vehicle model to interface with the external ESC model, in Simulink, Modelica standard library input and output classes are placed at the top level of our simulation. By connecting the outputs to the existing signal sources on the control bus, such as yaw rate and lateral acceleration, vehicle variables can easily be exposed to the outside when deployed as an FMU. The inverse, using input classes connected to signals with no source on the control bus, such as the ESC demand, enables control inputs to be fed into the vehicle from outside the FMU easily. This means that configuring a vehicle experiment from the VeSyMA libraries into an FMU with a bespoke input-output interface is a very simple task. For this case study, co-simulation using CVOD was chosen. There are two reasons for this. The first is that we desired the vehicle experiment FMU to run in Simulink using the Dymola solver for ease of use and deployment. The second is that this option is available to all Dymola users without needing additional license features. All results from the vehicle experiment with and without the ESC running within Dymola use the CVOD solver with the same solver tolerance as used in the exported FMU. During compilation, Dymola selects 97 states within the vehicle model and 15 states within the drive model for an experimental total of 112, making for a detailed vehicle model. All simulation conducted in Simulink use the default variable step auto solver with a default tolerance of 0.001. Our initial results are from the vehicle experiment simulation within Dymola, with and without an ESC model attached. These are plots of the yaw rate, plot 1, lateral acceleration, plot 2, and longitudinal velocity, plot 3. These demonstrate how, without electronic handling assistance, the vehicle begins to oversteer out of control in the second half of the test, as the vehicle is unable to complete the slalom course at the target speed. Our second set of results feature the vehicle experiment exported as an FMU without an ESC unit embedded inside it. This is run within Simulink and then run again within Simulink connected to a Simulink build of the electronic stability controller. Once more, plots of the yaw rate, plot 4, lateral acceleration, plot 5, and longitudinal velocity, plot 6, show that the vehicle cannot complete the test without electronic stability assistance as it oversteers out of control near the end. With results generated for the 4 test cases, we can now compare them to each other to better understand the effect of exporting the vehicle experiment as an FMU. These results compare the vehicle experiment with no electronic stability control running in Dymola and in Simulink as an exported co-simulation FMU. Observation of plots 7 and 8 in particular indicate that the detail as the vehicle oversteers over the grip limit are captured by both simulation methods. This is to be expected, as the vehicle model is run with the same CVOD solver in both Simulink and Dymola, thanks to the co-simulation option. Plot 9 shows a difference in minimum longitudinal velocity when the vehicle is most out of control. As there is no ESC present in this comparison, it is concluded that these small differences are the result of the Simulink variable step solver interacting with a CVOD solver exported from Dymola, particularly with regards to the event handling, given the location of the biggest disparity. Moving on to the comparisons between the experiment with ESC within Dymola and the Simulink ESC implementation connected to the FMU exported of the experiment, some small differences can again be observed. Generally, the vehicle model appears to be more unstable when controlled by the external controller within Simulink versus the internal controller in Dymola. This is shown by the high yaw rate in plot 10. Higher, very localized peak accelerations in plot 11, coupled with a higher yaw rate and larger drop in longitudinal velocity in plot 12 also suggest this. Although the trends between the two tests correlate, indicating the ESC is interacting with the vehicle in the same manner, there is enough difference in the result to warrant comment. Some element of this difference is likely to have been caused by the different refresh rate the internal Dymola ESC controller and the external Simulink ESC controller will have, owing to the different controller solver in these two tests. The next point to consider is the action of the ESC control on the actions of the solver in each environment. When combined within the same model in Dymola, any actions of the controller, such as zero crossing or state events, will trigger solver functions which affect the results and simulation of the whole vehicle model. Finally, it is worth remembering that the driver model within the experiments functions as a closed-loop drive model. Therefore, any differences in vehicle response will be amplified by a different driver model response. Analysis of the computational time of each test case indicates that the vehicle experiment ran comparably both within Dymola and within Simulink as an FMU itself. Whilst there is substantial time differential between the cases featuring an ESC controller, the margin of difference can be attributed to the extra simulation overhead associated with syncing the two models together during time integration. Potential actions to minimize the simulation time penalty include evaluation of various Simulink solvers, using a fixed step instead of a variable step solver, for instance, and optimizing the sampling and exchange rates between both the plant and the controller model. Given the differences in simulation results between the experiment in Dymola and with the Dymola ESC and the FMU deployed with the Simulink ESC, we can deduce that is the impact of the varying solver rates between the plant and the controller causing this significant time penalty. One option to remedy this would be to try and convert the plant FMU to run a fixed step solver at the same time step as the controller refreshes to minimize solver stopping and restarting overheads. Simulink allows the user to specify fixed sampling rates for parts of the model, and that would be applicable in this case. As the simulation speed was not of primary importance to this case study, no actions were taken to optimize the execution speed, therefore this can be assumed to be the worst case scenario when dealing with VeSyMA models. Fundamentally, this case study demonstrates that the vehicle experiments found within the VeSyMA library are suitable for being used as a distributed high-fidelity vehicle simulation solution. Whilst there are some significant time overruns found in this exercise, we are confident that actions taken to remedy them, as established in other literature, would be effective. Thank you for listening to our presentation. We are happy to answer any questions you have in the following question and answer session.